Unit 4, Vectors. Oh hey, look, I'm a vector, and I fit right inside of a V. Bam. Okay, so this unit on vectors isn't necessarily anything that's special or anything we haven't heard before. In fact, maybe you need a reminder. What is a vector again? Well, a vector, notice I have 3 blanks here for me to fill in. A vector could be anything that has a magnitude or a number or an amount or a value or anything that, a magnitude, a number, an amount. It's something plus, because if I just stopped there, I wouldn't be a vector, I'd only be a scalar. It's something plus a direction. And again, this is no new information that you haven't heard before. Some vector quantities you may have already heard. They should be familiar to you. We've talked about displacement. Remember, displacement was just the magnitude and direction from where you started to where you ended up. So if I travel along that path, if this is where I started and this is where I end up, then you could draw my displacement as just a straight line between those 2 points. We've also talked about velocity. It was a speed that was special. So call me speed, but with a direction. That's what velocity is. And of course, acceleration was a speeding up or a slowing down or a changing of a direction, but in a particular direction. And remember, force was a push or a pull that could have been to the right or to the left or down or up, but in any case, it had a direction. These are the 4 primary vector quantities that we've dealt with so far. You may see some associations with these with their scalar quantities, like displacement. Don't get it confused with distance. That is just a scalar quantity. It's how far you've gone. Or velocity, don't get that confused with speed. It's just a scalar quantity. It's just how fast you're moving in no particular direction. So, how do you represent a vector? The idea is nothing new, really. You've already been doing it, whether or not you realize it. This is how you represent a vector. It's an arrow in the direction of whatever vector quantity it is you're dealing with. This could be velocity. It could be acceleration. It could be force. It could be displacement. Any one of these. It's a vector. It's a magnitude in a particular direction, and from now on we're going to use arrows to represent our vectors. Now I should warn you, only really smart people can understand what I'm about to say. If you take a look at a vector, we can break it down like this. There's really a secret code that is implied with every vector that a physicist draws, and you need to be able to break that down. Here's the first secret. This arrowhead right here, that secretly tells you the direction of the vector. And this length of the arrow, well, that secretly tells you that vector's magnitude. In other words, how much, an amount, some number. So I could have a vector that was 35 meters per second and directed toward the east. Or I could have a vector that was, say, 70 meters per second and headed to the east. The magnitude is generally indicated by the length of the vector arrow, and the direction, no surprise here, is generally indicated by the head of the arrow. So we just got out of a unit that had a lot of images that looked like the following. Maybe a box on a table or a treasure chest on a floor. And we indicated all the pushes and pulls that were acting on that box by drawing arrows. Like, say, maybe this was the force due to gravity pushing it down into the ground. And this was the reaction force of the table that was trying to push it back up. And maybe this is the force and that is the force of 2 people trying to pull this box across the floor. And maybe this is the force of friction that's trying to resist them. When you add up all those vectors in your head, you can imagine maybe something like this. That the force due to gravity down and the normal force trying to push the box up would perfectly cancel out. And similarly, maybe one of those forces that you're applying would perfectly match up with the force of friction trying to resist it, and cancel out. And in this case, it appears as though there is only one person left standing at the end of the day. The normal force and the force due to gravity have canceled each other out, and the force of friction was canceled out with another force. And what do you know? I have a net force acting on this object. So when you combine forces, really what you're trying to do is see what's left over after forces cancel out. It could be forces, it could be velocities, it could be displacements, it could be accelerations, any vector quantity. When you combine them, could cancel out, and then you're just looking at what's left over at the end. 2 plus 2 equals 4, right? Well, sometimes, but not always the case with vectors. Just because you have a quantity of 2 adding to another quantity of 2 does not necessarily mean that they're going to completely add together. They would only do that if they were adding in the same direction. Sometimes 2 plus 2 would equal 0. Well, think about it. If you had a vector of 2 to the right and maybe a vector of 2 to the left, adding 2 plus 2 would effectively cancel each one out, and you'd have nothing. Consider the following two vectors. It's a vector of magnitude 3 and a vector of magnitude 2. These could be forces, they could be velocities. Like I said, I want you to get used to this idea that a vector could be any quantity that has a direction. So, let's say I'm interested in determining the maximum value of these two vectors. What is the most that I could possibly get out of these two vectors? Well, the most that you could possibly get is if those two vectors were acting in the same direction, like so. And anytime you have a 3 and a 2 acting in the same direction, well, you get a 5 acting in that direction. Now, sometimes you're going to have the situation where instead of adding two vectors, you'll be subtracting them. What is the minimum value that I could possibly get from a 3 and a 2? Well, that would be the situation where they were acting in the complete opposite direction. Like, well, this. In that case, the 2 and the 3 are going to be acting in the opposite directions, and therefore we will have cancellation, and there's only one guy left. It's that component, and he will be in the direction of the original vector. So when 2 takes away from 3, you're left with a vector of 1. So the most I can get out of a vector of 3 and 2 is 5, and the minimum that I can get is a 1. Yeah, 5 when they completely act together, 1 when they completely act in opposition, and anything in between those two numbers is a possibility that could result from a vector of a 3 and a 2. So I'm talking right now, I'm able to manipulate certain things, and then I talk about it, and then I hit. In order for you to get a better idea of this maximum and minimum value idea, what I'd like you to do is consider those same two vectors, a 3 and a 2, and the different arrangements that we can possibly get out of them. The way that I like to think about them is if the 3 and the 2 were vectors that kind of reminded you of a lawn chair that you'd lay on when you were sunbathing. And I want you to picture that this little circle right there in the middle is kind of like a hinge about which those vectors can rotate. Now, when that lawn chair is completely closed, you can see that the 3 and the 2, in this case right here, are completely laying on top of each other in opposite directions, and the only bit that's left over is this one little overhanging piece, which must have a value of 1, because the 2 and the 3 will cancel out. Now, as you were to open up that lawn chair, picture a piece of bubble gum that's been attached to one end of the 2 vector and the other end of the 3 vector. And as this piece is open, so say in this one, as those 2 vectors get open further and further, you can imagine that that piece of bubble gum is going to get stretched longer and longer. So from this case down to this case, as I keep opening up the lawn chair, you can see the bubble gum is getting stretched further and further. And from that case down to here, similar thing. And from that case over to here until the lawn chair is completely opened up flat, and now you have a complete length of 5 for that piece of bubble gum that was attached from one end to the other. What I want you to realize is that this maximum value, the 1 that was up here, that's the minimum value. It can't get any smaller than that. The piece of bubble gum attached from one end of the lawn chair to the other will not get smaller than 1, a length of 1. Whatever the vector is, like I said, a force, a displacement, a velocity, as long as it's a vector quantity. And when the 3 and the 2 are completely acting together, then the most you could possibly get, the maximum value, would be a 5. And any length in between 1 and 5 would be a possibility for those two vectors to result in. Okay, when you're adding vectors, there are two primary ways that you can do that. The first of those methods is called tip to tail, where we are going to call the arrowhead the tip and the part that doesn't have an arrowhead the tail. So if we were to add these two vectors to each other, this guy, which is kind of up and to the right, and this guy, which is just dead over to the right, we would do it like this. Take one of them, it doesn't matter which one, and bring it down, and take the other vector and attach it so that its tail is touching the tip of the previous one. Or, it doesn't matter the order you do it in, you could take this guy and attach the tail of the other to its tip. Either way will work. In any case, once you have attached those vectors tip to tail, all you would need to do is draw a vector that goes from the tail of the very first vector to the tip of the very next vector, and label it with a little r. That is your resultant vector. Now, I understand that you can't just go around taking these vectors and sliding them across your paper because you don't have this program that I'm using. But what you can do is you can try your best to approximate a vector that you see. So for example, now it's important for you to see that it doesn't matter the order with which I combine these two vectors. The resultant will still be the same length and in the same direction. Another thing that's important for you to realize is that this resultant vector is not a third vector. It's just the result of these two vectors coming together, falling in love, adding tip to tail, and making a baby. If I'm given a vector that looks like this on my paper, well, over here on the side, I'm just going to try to draw the same vector, the same length, and in the same direction. And if I'm trying to add it to another vector, say, that looks like this, well, I'm going to take that second vector and just try to draw the same length in the same direction, and then I'm going to draw my resultant vector from the tail of my first to the tip of my last. This is my resultant. Another method for adding vectors together would be called the parallelogram method. Let's take those same two vectors that I had in the previous example and add them together, but this time I'm going to use what's called the parallelogram method. To do that, instead of adding tip to tail, what I'm going to do is I'm going to take these two vectors and add them tail to tail. Yeah. And then what I'm going to do is I'm going to make it so that these two combine with two other lines to make a parallelogram. Now, in case you forgot what a parallelogram is a four-sided figure where opposite sides are parallel to each other. So, you see this guy? I want to give him something parallel to it. And I'm going to draw a line that looks like that. And you see this guy? I'm going to give him a line that is parallel and draw it like that. And then what I'm going to do is I'm going to cut off that excess amount, and I've given myself a parallelogram. From here, to draw the resultant vector, all you need to do is insert a line that is perpendicular, or rather that is the diagonal of this parallelogram, and that would be your resultant vector. Again, what I'd like you to see is that if I were to remove this resultant and get rid of those parallel lines, I could take these vectors and add them so that I could get the resultant vector that I would have gotten in the tip to tail method. It's going to be the same in either case. But what I want you to realize is that it should just make sense. If you were to think about the vectors as pulls or pushes, then if you were to pull something in this direction, and then if you were to pull it, say, in that direction, then it should make sense. Then you've net pulled it from there to there. Just think of these as real-life pushes or pulls, like you're sliding something across the floor. So, for example, we want to take this vector and add it to that vector. We could do that. First thing, we're going to move it. I like the tip to tail method. I'm going to take this first vector and I'm going to add it to the tail of the second vector. Or if you want, you can add the tip of the second vector to the tail of the first vector. It really doesn't matter. In the end, the resultant vector will always be drawn from the tail of the first to the tip of the last. This could be a velocity. Okay, if we had some velocity in one direction and a velocity in another direction, then this would be our resultant velocity. Or it could be a force, it could be anything. But what I want you to realize is it's the same as if you were to take some box, whatever the hell's in it, slide it over, slide it up, and wherever it ended up, it's as if you just walked it straight across to that position. That's the test to make sure that you're doing this in the right direction. Take that, slide it, and oh, if it's in the direction that you would have gone if you had just followed that resultant vector, then you're probably on the right path. Okay, so not everything in life is all about addition. Here we were given a situation where there's more than two vectors that you're trying to combine, and now we got this symbol here where we have to subtract a vector. It's okay. There's just a small trick for dealing with these. The trick to dealing with subtracting vectors is to do the same thing that you've been doing with adding vectors, except you add the opposite. And if that doesn't make sense, then maybe you've heard the term before of leave, change, opposite. If you have, then that's the same idea that we're going to apply to this. In other words, whenever you subtract a vector, what you do is you add its opposite. So if I am going to subtract this vector from the original value, then what I'm going to do is I'm going to add its opposite. And so if I take the tip of this and put it on the tail of that, and then take the tip of this, rather the tail of this, and put it on the tip of that, then I will have a resultant. Now this is looking kind of funky, so let me undo a lot of this stuff. In fact, I want to get rid of, because I want to replace you with you. And I want to replace that minus sign with a plus. Now, I can take this vector, drop it down anywhere, it doesn't matter, and take it, add it to the tail of that vector, and then take the second vector and make sure its tip is touching the tail of this next vector. And remember, the resultant is always drawn from the tail of the first to the tip of the last, and that is the direction that your vector will be indicated, with that magnitude as well. See the length of this arrow? That is the magnitude of your resultant vector. In other words, this guy's been hanging out over here and you've been kind of creeped out. Ooh. If I were to take this guy and move him from where I started, up here, down over there, and then move him up that direction, and then back down over here, I want you to notice that I've essentially displaced myself from my starting position to where I ended up by the length of that vector. So, consider the following. Bob the pirate is just landed on this island, and he has a treasure map that tells him the treasure lies somewhere on the other side of this waterfall river. Well, as you can tell Bob's not a good swimmer because, well, he only has one hand, and with one eyeball it makes it difficult as well. So instead of trying to forge the river, what he's going to do is he's going to take a different path to get to that treasure. To do that, instead of just going across, he is now going to go to the bridge, and then from the bridge, he will head across the bridge, and from that position, he will head over to the treasure. Consider the path that Bob has taken. He took a longer way to get there than he would have if he had just cut straight across the river. And what Bob has done is followed these component vectors to get to his final destination. If we were to consider these as displacement vectors, just consider if Bob were to go straight across, what that vector would look like. Maybe something like that. What I want you to realize is that these green vectors essentially are the same as this one big red vector in that they both end up at the same position. Adding these green vectors tip to tail, tip to tail, tip to tail, and done, drawing your final resultant vector from the tail of the first to the tip of the last, you have now an image of the resultant displacement, which is the vector quantity for Bob the Pirate. Do you know the pirate's favorite letter of the alphabet? No, it's not R, it's the C. Do you know how much it cost for a pirate to get his ears pierced? I hear it's a buccaneer. Do you know why the pirate went to the Apple store in the mall? He needed to get a new eye patch. I'm not sure if you're aware of this, but the only ships that pirates have trouble with are relationships. Okay, that's enough. I'm tired of being funny. Here's pretty much what I want you to take away from vectors. They indicate a magnitude and a direction. They could be anything that has a magnitude and a direction. Not just velocity, not just force, anything that has a magnitude and a direction. Though the primary vectors that we'll be dealing with are displacement, velocity, acceleration, and force. This direction could be indicated by a multitude of things. It could be left, right, up, and down. It could be positive and negative. It could be north, south, east, west. It could be, if you were thinking of an X, Y coordinate system, it could be a certain number of degrees from north, or maybe a certain number of degrees from south. So you could have degrees as a direction. Regardless, whenever you're combining these vectors, they will always combine from the tip to the tail of the next vector. And the resultant is always drawn from the tail of the first to the tip of the last if you are using the tip-to-tail method. The parallelogram method, it's out there. You can use it. I wanted you to see what it was all about, but I primarily use the tip-to-tail method. I like tips on tails. Lastly, I want you to realize that a vector has tangible meaning to the things that are associated with it. In other words, that arrowhead that's on your vector is always going to tell you the direction that your vector acts. And the arrow length is always going to be an indication of its magnitude. Up until this point, you've really just drawn arrows, not really considering their lengths. Obviously, you've given consideration of the direction, but the lengths really haven't been important to you. From now on, when we draw vectors, I want you to consider that a vector of that size is only going to be half the vector of that size in magnitude. Other than that, I want you to realize that if you have to subtract vectors, the best method to do that is to implement leave, change, opposite. That is, if you have this vector minus that vector, then you will leave this guy alone, you will change that sign, and you will add the opposite vector. Then, just add them as usual.